Conventional rudders, found on thousands of ships worldwide, represent a compromise between economy and necessity. Conventional rudders normally function satisfactorily for normal steering and course change requirements in open waters. The basic conventional rudder is efficient up to maximum 45 degrees. At higher angles, the rudder is not capable of maintaining a smooth water flow across both sides of the rudder, and the rudder stalls, i.e., loses its effect. If the rudder has its entire area aft of the rudder stock, then it is unbalanced. A rudder with between 20 and 40% of its area forward of the stock is balanced. Most modern rudders are of the semi-balanced design. This means that a certain proportion of the water force acting on the after part of the rudder is counteracted by the force acting on the forward part of the rudder. Hence, the steering gear can be lighter and smaller. There are several types of rudder designs. Click the hotspots to see the three most common types. This is the most used rudder type on ferries and smaller ships. The spade rudder provides good maneuverability. This type of rudder is most commonly used on bigger ships. It is not as effective as a spade rudder of the same size. The heel rudder is supported with bearings on the top and bottom, providing an endurable rudder construction. Conventional rudders are somewhat restricted when it comes to maneuverability at slow speed in confined waters. Several manufacturers have developed more efficient and advanced rudder systems the last 2 or 3 decades, and quite a few ships are now fitted with modern and more efficient rudders. Click the Rudders to see some examples. The flap rudder is different from a conventional rudder in that it utilizes an additional flap on the trailing edge for steering. This allows up to twice the steering power compared to a traditional rudder, translating into a much more maneuverable ship. The rotor rudder is essentially a conventional rudder, but with the addition of a rotating cylinder mounted vertically on the edge of the rudder. The purpose is to smoothen the water flow at high rudder angles, and thereby improve ship turning performance. The purpose of the T-rudder is to combine the advantages of the flap and rotor rudder in order to get the best possible rudder performance. The performance is indeed excellent, but unfortunately the price is high. Not many ships invest in this excellent rudder system. This is an alternative design to the flap rudder. The shape of the rudder is such that it can be turned up to 70 degrees and still retain excellent performance. The forebody of the rudder is elliptical in shape, but runs into a rear body section which is concave.
If a propeller spins quickly, it leaves a trail of bubbles behind it. As the bubbles pop, they make a lot of noise. These bubbles are not filled with air, but with steam. The steam is produced by the seawater boiling.
It is a well-known fact that water boils at 100 degrees centigrade. However, few people will know that at different pressures, the water will boil at different temperatures. If you increase the pressure, as in a pressure cooker for instance, then the boiling point of the water increases. Hence, the cooking is more efficient. Few people will know, however, that at reduced pressures, water will boil at lower temperatures. I have here a vacuum pump, and I'm going to turn on the vacuum. This flask here contains water, and we have it connected to a pressure gauge, and we're reading at the moment approximately 15 pounds per square inch, which is 1 atmosphere. I turn on the pump, you notice the pressure dropping immediately, and as the pressure drops, as we approach zero, bubbles start to form, and the water starts to boil. So here we are at room temperature, but at a significantly reduced pressure, almost a complete vacuum, the water is now boiling. Water boiling at 20 degrees centigrade at almost 0 pounds per square inch, a remarkable phenomenon, sir.
When a submarine's propeller turns quickly, an area of low pressure is created on the blades. This lowering of pressure causes the water to boil without heating up and produces bubbles of steam. This is called cavitation.
The formation of those bubbles is dependent on how fast we rotate our propeller. So the faster we go, the more risk we are for cavitation.
The Pennsylvania's propeller design is a closely guarded secret. But the basic principles of a quiet running propeller are known. Cavitation only occurs when a propeller spins quickly. Slowing the propeller down reduces cavitation and therefore noise. But slowing the propeller also reduces a submarine's thrust. To overcome this problem, the Pennsylvania's engineers developed a unique propeller with 4 additional specially shaped blades. These generate large amounts of thrust, but at much lower speeds. This way, the Pennsylvania produces almost no cavitation or propeller noise. She is a silent predator of the deep.